Alright, so in this video we go over section 6.5, which is properties of logarithms. So in this case, in this section we are going to work with the properties of the logarithms, that is a product rule, the quotient rule, and the power rule. And then we are going to apply those to write logarithmic expression as a sum or difference of single logarithms, and write a logarithmic expression, a group of logarithmic expressions as a single logarithm. And then we are going to introduce the change of base formula to evaluate logarithms that are base whose bases are neither 10 or nor e. Okay, so let's begin with the properties of logarithms. So we are going to have essentially three rules. Of course there's more, but we are going to start with the three basic ones. The product rule, so the one that tells us that the logarithm of the product of two arguments, we can write it as a sum up to logarithms. For example, if I have log base 3, for example, and then 5x, this is the same as saying logarithm base 3 of 5 plus logarithm base 3 of x. So we split it into a sum. And likewise, we can do the reverse. If we are given a sum up to ln of 5 plus ln of z, for example. So we have two logarithms adding together. We can write one single log and multiply 5 times z. So either way. And then we have the quotient rule, in which the logarithm of a quotient is, instead of the sum, it's going to be the difference. For example, logarithm of, I don't know, maybe x over 5, for example. This is the same as saying log of x minus log of 5. And likewise, if we do the reverse for this, we can have a log base 3 or whatever base. Well, let me change it. Log base 7, why not? Log base 7 of, let's say, r, whatever letter, it's fine, and minus log base 7 of 3. So we end up with log of the quotient between r and 3 on the base 7. So that's pretty much how these work. Alright, so the power rule. For the power rule, I have a special name for it that I like using. Well, it's not mine. I learned it from another professor in the past. I like to call this the smackdown base basketball rule. All right, so if we do the rule, if we apply the rule this way, we're going to do the smackdown rule. Because this R, what it does essentially is to jump in the front, like smackdown. Otherwise, if we apply the rule in the backwards way, okay, let me find a good color, a contrasting color. All right, I'm gonna use, if we do it the other way around, this is the basketball rule. Because what do we do with R? It's gonna jump like in basketball and become the power of m. Okay, so for example, let me give you a simple numerical example, like log base 5 of x cubed. So in this case, we're gonna do smackdown here. So smackdown, I used blue for smackdown. and make it jump into the front. 3 log base 5 of x. On the other hand, what if I have 7 ln of y? In this case, this 7 will jump as a power of y. That's the basketball rule. Ln of y to the 7th power. So we are going to combine all this in different examples here. So write a logarithmic expression as a sum or difference of logarithms. That's the next step. Alright, so write each expression as a sum and or difference of logarithms. Express powers as factors. In other words, use the smackdown rule. All powers, be sure to write them like factors, like the third rule. Okay, so what do we have? So we have log base 5 of u cubed times v to the 7th. Alright, so the most prominent rule that we think we're going to use is the product rule, because we have the product between those two factors, u cubed and v to the 7. So what I'm going to do here is log base 5 of u cubed plus log base 5 of v to the 7th power. And then while they're asking us to express powers as factors, in other words, use the smackdown rule, so the 3 goes to the front, the 7 goes to the front. Okay, let me use a different color to illustrate that. Okay, so we're going to end up with 3 log base 5 of u plus 7 log base 5 of v. Final answer. Alright, let's do another example. So for an example like letter B, so there's a bunch of different ways that you could go about this one. For example, you might want to distribute the 2/3 to the x and to the e to the x. However, if we do that, that's going to be a lot of work, because then we will have to do 2 smackdowns, while from the very beginning we can avoid a lot of work and do that smackdown rule from the very beginning. That's going to give us 2/3 ln of x divided by e to the x. Alright, so now that we have this ln of x divided by e to the x, we are going to use the quotient rule. We have the quotient that turns into a difference. Alright, so we're going to have ln of x minus ln of e to the x. However, don't forget these 2/3 that we have here, multiplying as a constant, which we will later distribute, but not yet, because there's another rule that you want to use in order to simplify this a bit further. So from the previous section, remember, ln and e are inverses to one another, so we can cancel those two out and have 2/3 times ln x minus whatever is left in this case, which is just x. So here we may now distribute the 2/3 to get 2/3 times ln of x minus 2/3 of x. Final answer here. Alright, let's see what's on the next page. So the next page will give us pretty much an example that will combine all of the rules, many rules here, even algebraic techniques from earlier in the semester, or even previous algebra courses. You'll see. So again, look at this power right here, this cube. Alright, so if you were thinking of raising this y squared minus 9 to the third, and possibly expanded binomial cubed, and then 7 cubed, y cubed, and then the radical cube. Don't do that because that's going to be overkill here. So what are we going to do in this case then? Well, we are going to use the smackdown rule. I'm going to have this 3 and make it jump to the front. So 3 log base 7 of y squared minus 9 divided by 7y, square root of y, this should have been squared, plus 2y. Alright. What is it going to be there now? Well, here we have a really big expression that we are going to do, that we are going to simplify one step at a time. So first of all, we have a quotient. So we're going to use the quotient rule. So for the quotient rule, we're going to do the following. Log base 7 of y squared minus 9 minus log base 7 of 7y times the square root of y squared plus 2y. Okay, hopefully so far so good. However, don't forget this cubed. Okay, read out. Alright, so what am I going to do next? I'm going to distribute this 3 over here and over here. So that's going to give me 3 log 7 y squared minus 9. I know what you're thinking. You have a difference of squares. Yes, we're going to deal with that difference of squares soon, actually. So 7y square root of y squared plus 2y. Okay, let's see what can we do afterwards. So yes, I'm going to factor this difference of squares. And over here, 3 log of x. Oh no, that's not an x, that should be a y plus 3 times y minus 3 on the base 7. And well, I'm gonna keep this for now because, well, number one, I'm running out of space here and I want to make sure everything fits in here and that I use the subsequent rules correctly. So for now, I'm gonna leave it as 3 log base 7 of 7y times the square root of y squared plus 2y. Alright. What are we gonna do next? Well, so notice this product of arguments here. We can use the product rule. This will be 3 times log base 7 of y plus 3 plus log base 7 of y minus 3. Okay. And now over here, I'm going to have, look at this. I'm going to have the product of 1, 2, and 3 factors. Of course, if we go back to the original rules, well, the rule has only the product of two arguments. However, this can be extended, of course, to something like log of PQRST, that's log of P plus log of Q plus log of r plus etc etc. It can be extended to as many factors that we have. And that's what we're going to do here. Take advantage of that in order to break this up into so minus 3 open brackets, because here we're going to have the sum of 1, 2, 3 logs. Log base 7 of 7. I know what you're thinking here. This is going to simplify really nicely. Log base 7 of y and log base 7 of the square root of y squared plus 2y. Alright, hopefully I haven't lost you at this moment. Alright, so what are we going to do? So number one, so yes, we can simplify this, but let's save it for a second so the distribution is easier to visualize. Over here, over there, and finally over there. So let's do all the distributions. We're going to have 1, 2, 3, 4, 5 total terms. So 3 log base 7 of y plus 3 plus 3 log base 7 of y minus 3 minus 3 log 7 of the number 7 and 3 log base 7 of y plus 3. Well, actually, careful here. This is not supposed to be plus. This is how these were supposed to be minuses. Okay, minus 3 log base 7 of y, the square root of y squared plus 2y. Okay. What else can we do? Okay, number one, in the first place, I'm going to do something in an effort not to write the whole thing. You might want to correct this part of the process. I'm going to change this to radical form. Instead of having the radical, I'm going to write this to the 1/2. And here I'm going to do two movements actually. Number one, I'm going to cancel log base 7, oh not this one, log base 7 with 7. That reduces to 1, but 1 times negative 3, this is going to be negative 3. Okay, equals 3 log base 7 y plus 3 plus 3 log base 7 and then 1 times negative 3, and then minus 3 log base 7 of y. So this dashed line in purple shouldn't be there. I made a mistake. I wanted to cancel this one right there. And this is what I'm going to do here. I'm going to smack down this 1/2 and multiply with a 3. 1/2 times 3, this is going to be minus 3/2 log. And look what I'm going to do here. I'm going to factor out the GCF. This is going to be y times y plus 2. Okay. So what are we going to do there? Okay, we are going to do another product rule for logarithms, which in this case, well, I'm afraid I'm not going to have enough space. Well, I'm going to try my best. 3 log base 7 y plus 3 plus 3 log base 7 y minus 3 minus 3 and then minus 3 times log base 7 of y. And in this case, okay, I'm going to break this up on the side. Right here, I'm going to use a different color. I'm going to use black. So this guy becomes log of base 7 of y plus log of y plus 2. Okay, and then when we multiply that by negative 3/2, I get this get each of these two multiply by negative 3/2, so minus 3/2 log of y and minus 3/2 log of y plus 2. Okay, is there anything else that we can do perhaps? Well, since I'm running out of space here, I would like you to observe these two. Log base 7 of y, log base 7 of y. They are like terms, so negative 3 minus 3/2. Let's see what do we get. So I get 9/2. So this is what I'm going to do. I'm going to erase this 3. I'm going to make it 9/2. And over here, I'm going to fix this. I'm going to erase this and do it like this. And this will be our final answer. All right, yes, this is one huge example that pretty much puts everything in action. Some factoring, rational powers, radicals, and some of the older, well, not really old, some of the properties that we learned in the previous section, etc. Now let's do the opposite. Let's do this backwards. And now we're going to write a logarithmic expression as a single logarithm. So these two are logarithmic expressions. They're asking us to write them in terms of a single logarithm. So the first thing we do is observe these coefficients. These coefficients will become the powers of each of the arguments, aka basketball rule. Okay, so log base 4 of y to the third power plus log of base 4, log base 4 of z to the fifth power. Now notice we have the sum of two logarithms. When we have the sum of two logarithms, we can have only one logarithm with the same base, provided we just write the product of these two arguments. Final answer. All right. Now, what happens when we have a bunch of terms, like more than 3 terms or even more than 4, and some of the signs here, the most important thing is the signs are going to matter here. And because the homework, the quiz, the exam is going to give you the terms like all over the place in terms of what their signs are. So my advice here, rewrite the whole thing, but write the positive terms first and then the negatives afterwards. I'll show you why do we do that. So I'm gonna write the first positive without doing any basketball rule. I know it's kind of obvious that this is gonna be jumping. This one is gonna be jumping as well. Let's hold our horses here, and plus 1/2 ln and then the negative ones, minus ln of 9 and minus 2 ln of x minus 4. Right? Because the first thing we do, just the same way we did it with the previous example, basketball if applicable. So this guy jumps as a power, this guy is going to jump as a power, and the number 2 is going to jump as a power. Okay, I know what you're thinking. Do we do to the negative 1 power? I mean, technically that's possible. That's not incorrect, but that's not, well, that's gonna make it a little bit hard to understand and follow. So I will just keep the negatives. You'll see what am I gonna do with them. So this will be ln of x cubed plus ln of x squared plus 25 to the 1/2 minus ln of 9, and then minus ln of x minus 4 to the 2nd power. Okay, so again, these powers jumped to their corresponding arguments. All right, now, so the reason why I advise to have the negatives at the end is because I'm going to do the product. I'm going to use the product rule with these positives first. So these two ln's, I'm going to have them in one single ln in the following form. Ln of x cubed times x squared plus 25 to the 1/2. I know what you're thinking. This 1/2 can be rewritten in the radical form. Yes, we're going to do that. But before doing that, what I'm going to do is factor out the negative sign. I'm going to factor the negative sign. I'm going to be left with ln of 9 plus ln of x minus 4 to the 9th power. I mean to the 2nd power, not to the 9th power. Part in there. So the reason for which I asked you to do the negatives at the end is to make that negative a common factor, and so we can easily see this sum and turn it into a product by using the product rule. So I'm going to turn this 1/2 power into radical of index 2, ln of x cubed times the square root of x squared plus 25 minus the ln of this product, of the product between 9 and x minus 4 to the 2nd power. Now notice how this expression has been almost simplified into a single quotient. I mean into almost one term. So in this case we're going to use the quotient rule, and the reason for that is because we have a negative sign here. So ln of m minus ln of n, we write ln of m over n. That is x cubed times the square root of x squared plus 25 divided by 9 times x minus 4 quantity squared, and this is final answer. All right, so this is pretty much what we do when we write logarithmic expressions into more than one logarithm, or backwards, we are giving a bunch of terms, put them together into a single one. All right, so now let's evaluate logarithms whose base is neither 10 nor e. All right, so what's essentially the whole principle here? So sometimes we will be in the need of evaluating logarithms like this one, for example, log base 3 of 5 or log base 17 of 93. You know, bases that are not 10 or e. That is, it's not just a log or it's not ln. And in many cases, well, the thing is, not all calculators are able to evaluate those expressions. For example, this calculator is able, so If you're lucky and if you have this function, you go to you click on math and then go under, I believe it's num, go down, go up a few. No, it's not the num, it's actually the math, and then you will have the log base. Not all calculators have it. This one does. So all we do, this is really easy. Log base 3 of 5, and boom, you get the final answer. But again, not all calculators have this ability. Most calculators typically have the log, which is log base 10, and ln, which is log base e, which is the natural log, and the common log. So we are going to use the change of base formula to convert these weird looking bases into known bases. For example, this log base 3 of 5 can be rewritten in the following form. So let me describe the formula. So we have log base a of x. We divide log of x over log of a. You can think of the quotient between the logs of x and a, just like this, just in this order. So log base 3 of 5 can be rewritten as log of 5 over log of 3, or ln of 5 over ln of 3. Let's find out if that's true. Okay, so I'm going to do the log version. Log of 3, wait a minute, no, log of 5 divided by log of 3. We should get the same answer here. Surprise, surprise. ln of 5 over ln of 3. Whoops, I forgot the division. ln of 3. Same answer, either way. So you can change a logarithm with a weird base that it's not on your calculator, but you can change those to log base 10 or ln. Either way, look, you get the exact same answer. Alright, so we have a couple of examples here. I mean, even though I already made up one. So let's look at log base 9 of 13. So there's two ways to evaluate this guy. So number one, or letter A, well, let me use I. This is okay, log base 9 of 13 equals log of 13 divided by log of 9. Or the second way, log base 9 of 13 is the same as ln of 13 over ln of 9. Okay, let me do that in the graphing calculator. Okay, let me clear all of this. So I'm gonna go math num. No, it's math again. Log base, and the base is 9 and the argument is 13. I get 1.67. Okay, so I'm going to round to 4 decimal places. So this is going to be 1.1674. Okay, I'm going to round 4 decimal places. Now I'm going to use the change of base formula with log. So log of 13, close parentheses, divide by log of 9. See how we get the same number? Even if we do the ln of 13, close parentheses, divide by ln of 9, close parentheses, same number, same result, either way. Now, let's approximate the other one. Well, using the change of base formula, well, again, there's two possibilities. One is log of the square root of 7 divided by log of the square root of 3. Else, you can use ln, natural log of square root of 7 over ln of square root of 3. Let's see what we get for this. So ln of square root of 7, I'm gonna do the ln only. I mean, we should get it the same for the three versions. So ln of the square root of 7 divided by, whoops, let me delete this parentheses and put it outside, divide by ln of square root of 3 and close parentheses, and boom. This is approximately 1.7712. The 4 is not good enough to round it to the 3, so we keep it like this. All right. Alright, let's use the properties of logarithms to find the exact value of each expression. Do not use calculators, even though you can punch this in calculators. Okay, you are in the exam or a quiz or something, you will be expected to show all steps. If you give just the final answer for this, well, that means you either use a calculator or something, which in this case the idea is that you use the properties of logs that we have learned in this last couple of sections. Alright, so in this case we have log base 6 of 9 plus log base 6 of 4. So we're going to write this log base 6 of the product between 9 and 4. But 9 times 4 can be reduced to log base 6 of 36. And you might remember how to evaluate this from the previous section. We are going to write the number 36 as a base 6. That's 6 squared. And then the idea is to make these two guys match, this guy and that guy, and boom, boom, goodbye. Final answer, 2. For the next example, 5, we have the expression 5 to the log base 5 of 6 plus log base 5 of 7. So the exponent 5 remains there. Because of this addition symbol between two logarithmic expressions, we could write that logarithmic expression with the base 5 of 6 times 7. I know what you're thinking. You can cancel this because they match, but let's simplify this. 6 times 7, which is 42. Yes, this exponential base matches the logarithmic, the base of the logarithmic, so goodbye. They cancel out. Okay, 42 is final answer. The next one is going to be an interesting one. Well, here we have the product of two logs. The product of two logs that actually have different bases. Okay, how are we going to deal with this? Well, let's see. So number one, I'm going to do the following. I'm going to put parentheses around this guy just to denote the product in a better way. And then what I'm going to do is this entire logarithm, I'm going to make it the exponent of the other log. Right? The idea of that, what I'm doing essentially is the basketball rule. So I'm going to have log base 8 of 9 raised to the power log base 3 of 8. Alright, what am I going to do here? I want to simplify this. We're looking logarithmic power of some weird log with a weird base that has a weird argument. And the good news here is we can work on this 9 to make it match with the base, so we can cancel. Remember, we can cancel like this, boom boom, as long as the number 9, and as long as we have both the same number, this exponential base and the base of the logarithm. And in this case, well, we have a 9 and a 3. However, we can work on the number 9 to make it look like a 3. That is log base 8 of 3 squared. I'm going to put parentheses around, and then I'm going to put the power log base 3 of 8. All right. I know what you're thinking here. Well, we're almost there. We're almost there. So, but before we proceed, let's recall one of the properties of exponents. One very important that tells us that when we have a to the m and that raised to the nth power, we multiply the powers. Right? In other words, I'm going to multiply this power with that whole power in the next step. So logarithm base 8 of 3 to the 2 times log base 3 of 8. And I know what you're thinking. You might be thinking here of canceling these 3 here and there. However, no, we can't do that. In order to do that cancellation, this log and the exponent must be free of coefficients. So before canceling this exponential with this log base that matches actually the base of the exponential, first we have to basketball this coefficient. So once we basketball this, we get the following: log base 8 of 3 to the power log base 3 of 8 squared. And well, you might want to square the number 8 to give us a 64. However, look at the base down here. That's going to cancel as well. So that's what I'm going to do now. I'm going to cancel the exponential base 3 with the logarithmic operator base 3. And we are going to be left with log base 8 of 8 squared, which these two match. They can be cancelled safely to get a 2 as a final answer. All right. So what are we going to do next? So let's look at the next example. All right. The next example, it's a very interesting one because, well, it looks a bit weird when it comes to observe the base of the exponential and the base of the logarithmic at the top as the exponent of that exponential. What's weird? Well, or how are these related? Well, if we observe, this base is only e. However, the base of the logarithm in the exponent is a square power, right? So we wish we had this number 1. We wish we didn't have that 2, so we can just boom boom cancel. Or otherwise, we wish we have our exponential base to be e squared so they can cancel. That we can make it happen. Okay, so I'm going to let's see. I'm going to rewrite this as e. I'm going to leave some space here for some little trick that I'm about to do. Log base e squared of 9. So again, eventually what we are going to do is to cancel this e potentially square with this log e of log base e square, but we cannot do that yet because we don't have that too. The thing is, I cannot just put it in there. Yes, I'm gonna put it in there, all right? However, for now, I'm going to write a power 1. I know this is kind of obvious and unnecessary to have these parentheses and this one, even though this is exactly, we can argue about that this is exactly as what we have in there, but adding these parentheses and adding this one as a placeholder has a really huge purpose in here, because this number one, the number one, you can write it in many different ways. For example, the number one could be 2 over 2, 3 over 3, 573 over 573, pi over pi. I don't know. Your favorite quotient of numbers, I mean, that reduces to 1. Which one are we going to use? Okay, one that help us to serve our purpose here, which in this case, I'm going to write this one as e to the I'm going to use 2 halves. 2 halves. Hopefully we all agree that 2 halves equals 1. Okay? And then what I'm going to do, I'm going to break up these 2 halves. And, well, you'll see what I'm going to do. So this is going to be the number 2 halves, just like any other fraction. Let me write it over here. 2 halves is the same as saying 2 times a half. Just the same way 3/3 is the same as 3 times 1/3, and so on and so forth. All right. So I'm gonna do the same thing there. So I'm gonna write this as e to the second power e to the 2 times 1/2. All right. Raised to the log base e to the second of 9. All right, now I'm gonna play with these powers here. So let me recall this properties of exponents when we have a to the mn, which is what I essentially have here. I have some a to the mn. This is the same as a to the m to the n, or this is also the same as a to the n to the m. So in this case, it doesn't matter. You could leave the m inside and the n outside, or the n inside or the m outside, and this comes from the commutative property of the multiplication. So either way, it's going to be fine. However, we are going to pull outside the one that it's not going to be helpful in this case. So in this case, what we are trying is to match this e squared, which is the base of the log, with the base of the exponential. So the one that is going to go outside is going to be the 1/2. So I'm going to have e squared times, raised to the 1/2 times log base e squared of 9. Okay. What am I going to do next? I'm going to do basketball here. I'm going to have that 1/2 because, yes, we finally match the exponential base with the base of the logarithmic factor here. However, we cannot just yet cancel them. We need to make sure this log doesn't have any coefficients in the front. Okay, so the next step is going to be e squared raised to the log e squared to the 9 to the 1/2 of 9 to the 1/2, sorry. And now we may cancel this. We may go ahead and do that. And I'm going to be left with 9 to the 1/2, which is the square root of 9, which is a nice number, 3. All right. Let's move on to the last example in this page. So they're asking us to evaluate log base 2 of 4 times log base 4 of 6 times log base 6 of 8. All right, that's going to be an interesting one to work on. However, how are we going to solve this one? Well, we had a situation in which we have the product of logs with different bases over here in example C. All right. However, if we do the same technique, the same strategy of basketballing this first factor, that is, send this log base 2 of 4 to the top, notice we won't be able to have this 6 to match this power 2 because the number 6 is not a power of 2. So in this case, this is not going to work. That strategy is not going to work. Well, I'm gonna continue down here. So I'm gonna do something else. I'm going to use the change of base formula. And I'm going to put it at the top here at the top, so you can see how it's going to work. And it doesn't matter, again, if you use common logarithms or log base 10 or ln. I'm just going to use ln because it's shorter to write. So ln of x over a, in this case ln of 4 over ln of 2 times ln of 6 over ln of 4 times ln of 8 over ln of 6. See what's going to happen here? A bunch of cancellations will occur. I will be able to cancel ln of 6 with ln of 6 and ln of 4 with ln of 4. What am I going to be left with? Well, I'm going to be left with ln of 8 over ln of 2. All right. We are essentially done with this simplification. However, this can go a bit further and we are going to end up with a really nice number, because in this case the number 8 can be written as a power of 2, that is ln of 2 cubed. And notice this ln with this ln of 2 with this ln of 2 can be potentially canceled, but I cannot just cancel them yet. First, what I'm going to do is smack down the power 3 ln of 2 divided by ln of 2. Now we're good to go and cancel ln of 2 with ln of 2. Final answer for this, another 3. All right. Let's see. All right, so now that we have some practice with with properties of logarithms here, let's use those and put them together to solve equations. So actually, well, yes, we're essentially solving an equation, but we have a bunch of terms, and we are going to use that information to express a given equation as a function of x, in which y will be the dependent variable and x will be the independent variable. All right, let's see how we're going to go about this. So first of all, ln of y equals, do you recall the advice I gave you earlier to write the negatives at the end? 3 ln x plus ln of c minus ln of x plus 4. So I'm gonna do the basketball rule here. These 3 will become the power. Ln of y equals ln of x cubed plus ln of c minus ln of x plus 4. And then we can put this together as one single log. Ln of cx cubed minus ln of x plus 4 equals ln of y. And then we could put this together using the quotient rule because we have a difference of two logs. So we can write it as a single log of cx cubed in the numerator and x plus 4 in the denominator, and then ln of y on the right hand side. And at this point, notice we can just get rid of the ln's. For now, let's just do it like this. Get rid of the ln's, and y equals cx cubed divided by x plus 4. Alright, so for the previous step, essentially what I'm doing is doing the inverse of ln, which is exponentiate both sides to cancel the ln's. But we're going to go into more detail when we do the next section. Alright, now let's see. Ln of y plus 4 equals 5x plus ln of c. So let's see what are the difference between these two exercises. So, exercise A, for this example 5, all of the terms have a natural log operator. However, one of the terms right here is missing the ln. So let's see how. In this case, I can't use the product rule for logarithms, and the reason for that is because this 5x doesn't have an ln. However, can I put an ln? Can I rewrite this 5x in a way that it has an ln? Yes, of course, we can do that. How can we do that? Well, let me get a piece of scratch paper so I can do that for you. So, you might recall a couple of the properties that we did when we have log base a of a to the x. These guys cancel and we get x. The other property is a to the log base a of x. Essentially these cancel and we get x as well. Let me give you a few examples. So when I have log base 5 of 5 to the x power, boom boom, they cancel. This is x. 7 to the log base 7 of x squared, boom boom, this cancel, I get x squared. Alright, what we did so far is go from here and simplify. But what if I want to, in a way, unsimplify? That is, rearrange a term to make it look like something that will be useful for our purpose. For example, what if I have, I don't know, y cubed? Okay, y cubed. The quantity y cubed is equivalent to, say, log base 13 of 13 raised to the y cubed, because if we cancel these two, we get y cubed. Y cubed is the same as saying 7 raised to the log base 7 of y cubed. If we cancel these two, we get this y cubed again. Okay. Y cubed is the same as saying ln of e to the y cubed. And that's because if we cancel ln with e, we get back to y cubed. And finally, y cubed is the same as e to the ln of y cubed. And the reason for that is because, boom, boom, we can cancel these two, ln with e, and get simply y, cubed. Okay? So we are going to use this idea to rewrite this 5x in a way that a natural log shows up there. How are we going to do that? Well, I'm going to do the following. ln of e to the 5x like this. And so we do this sort of trick. Well, it's not a trick, it's algebra ultimately, but I mean, since it's not the type of operation we do like every day or all the time, so that's why we typically call it a trick. So that's the trick, if you will. So now we have two natural logs separated by as an addition sign. That means we write one ln and the product of the two. All right, and I'm going to cancel these ln's by exponentiating both sides. Boom, 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 boom. And I'm going to get y plus 4 first equals c e to the 5x. And to get y by itself, all we do is subtract 4 to both sides. That is, y equals c e to the 5x minus 4. Final answer. Very typical exam questions are like example 6 and 7. Interesting. Show that log base a of this term, of this humongous mess, plus log base a of that humongous mess equals to 0. So how are we going to do this? So in order to do, when you read the word show, you don't plug in values to see if it works. What you do is simplify one side of the equation given and show that we get the exact the exact quantity that is found on the other side. All right, so what are we going to do here? Looks like really ugly at the beginning, but once we start doing the steps, a lot of familiar familiar forms will be coming to play. All right, so I'm going to, first of all, we have a log plus another log. That's the sum of two logs. We are going to use the product rule when we have log of m plus log of n. This is the product rule, log of m, and of course base a, I omitted it, but it's still the same. Okay, so I'm going to write a single log, base a, square root of x minus the square root of x minus 1 times the square root of x plus the square root of x minus 1. That equals to 0. Okay, so you might, when you observe this expression, you might want to observe the following. This has the following form. A minus b times a plus B. Where have you seen this before? Difference of squares. So log base A of the first guy squared, the square root of x squared minus the second guy squared. All right. So what is going to happen here? Cancel, 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 cancel. And we are going to get log base A of x minus 1. And be careful here with the negative signs. Okay? Be very, very careful here. So, the next move will be to distribute the negative sign. That's going to give us the following. So I'm going to continue here. That's going to give me log base A of x minus x. Negative times a negative is plus 1. Okay, notice how these x's cancel. So the only term that survives here is the number 1. Log base A of 1 equals 0. So again, we discussed in the previous section that log of 1, regardless of the base, whether this is ln of 1, log base 10 of 1, log base 7, this is 0, which in this case matches the other side. So this is how we show that this statement is true. All right. Example 7, show that ln of 1 plus e to the 3x equals 3x plus 1 plus ln of 1 plus e to the negative 3x. Okay? And we are going to do this in two different ways. Right, two different ways. So number one, the one way that I'm going to do, I'm going to work with the left hand side and I'm going to make it look like the right hand side. The other way is I'm going to work on the right hand side and I'm going to make it look like the right hand side. That's what I'm going to do here. So how do we proceed here? Okay, so it looks like the left hand side, sorry. It's already simplified in lowest terms and we cannot do anything about it. Well, yes, at simple glance, if you're thinking about it, yes, that is true, only at simple glance. Now, somehow I have to end up with some e to the negative 3x, like on the right hand side. How are we going to do that? Well, we are going to do some sort of a trick. Remember the trick of writing the number 1? 1 is equal to x over x, y equals to 3x to the 7 over 3x to the 7. That's also a 1. 1 equals ln of y over ln of y, and e to the 3x over e to the 3x. Why not, right? Cancel these two, you get the number 1. And that's the strategy that we are going to employ here in order to make the left hand side look like the right hand side. Okay, and I'm going to work with that 1. So ln is a number 1, the one way. Ln of 1, I'm going to write that as e to the 3x divided by e to the 3x plus e to the 3x. And on the right hand side, I'm just going to write 3x plus ln of 1 plus e to the negative 3x. Okay, so why are we doing this? Because if you observe this, e to the 3x and e to the 3x will be the GCF. We can factor that out. ln of e to the 3x times 1 over e to the 3x plus 1. And the right hand side remains the same. Alright, so let's see what's next. Notice the following. Number 1, I have the product of two arguments. That means we can use the product rule. And at the same time, I have this quantity in the denominator that I can move up to the numerator with negative exponent. So I'm going to do the two things in one shot. Number 1, I'm going to break this up into two ln's. And at the same time, I'm going to move this to the numerator, e to the negative 3x plus 1. 3x plus ln of 1 plus e to the negative 3x. Okay? Now, there's two things I'm going to do now. Notice I have e to the negative 3x plus 1, and over here I have 1 plus e to the negative 3x. In this case, the order of the terms is not going to matter, but I'm going to write it just so it matches what I have on the right hand side. Wait a minute, I didn't do that, I'm afraid. What am I thinking? So I'm going to have 1 plus e to the negative 3x. And over here, see how ln and e cancels? And give us only the 3x. And don't we have the same thing? Isn't it true? That's one way. The second way, number 2, I'm going to work on this side now. I'm going to keep ln of 1 plus e to the 3x equals 3x plus ln of 1 plus e to the negative 3x. But instead of having the 3x, remember what I did on the example above? I did a trick of adding ln of e to whatever quantity. I'm going to employ this same trick to have ln of e to the 3x. This way, we are going to have a sum of two ln's, which can be written as a product right? And then from here, I'm going to see, notice on the way 1, I was working only on the left hand side. On the way 2, I'm working on the right hand side. The left hand side still remained the same. So what I'm going to do next, I'm going to distribute these two. ln of e to the 3x plus e to the 3x times e to the negative 3x. I'm going to take care of this negative sign. I'm going to send this to the denominator of e to the 3x with positive exponent. But these two reduce to 1, isn't it? Which in this case, it's going to leave us with e to the 3x, boom, plus 1. Yes, the order is not the same, but it's the same thing. 1 plus 2 is the same as 2 plus 1. The commutativity of the sum of two terms, so ln of 1 plus e to the 3x, if you want to write it like that, and conclusion, these are the same. All right, and I think this is a good moment to quit. I'll see you on the next video.